Hi everyone, let's talk about Wilson's theorem in modular arithmetic. The general idea is that if we were to take n factorial, then it'd be congruent to 0 mod n, and that's because there's a factor of n over here. So next what we look at is n minus 1 factorial, and we want to look at what the residue is modulo n. And this is a natural question to ask because this consists of all the non-zero residues that are less than n, so 1, 2, 3, all the way through to n minus 1. So excluding 0, this is a complete residue system, and we want to find out what the product of it is, what remains of it modulo n. So I'll tell you what the result is. In general, what's true is that if n is greater than or equal to 2 and it's an integer, then n minus 1 factorial has several cases, but there is a large degree of regularity to it. So it's negative 1 mod n if n is prime. And that's the case that's usually stated, but we're going to do a complete classification. It's 2 mod n if n is 4, and 0 mod n if n not equal to 4 is composite. So you can see that it basically boils down to the prime case and the composite case, but the 4 case is a little bit different. So it is true that it's negative 1 if and only if it's prime, but as you can see, there's more to the story than just prime and composite. There is a special case with 4. So let's prove this. There's going to be lots of casework here. More casework than it might seem at first, because there's a bit of a nuance to it, which we'll see in just a second. So first of all is if n equals to 2, we're taking care of the even prime first. Then n minus 1 factorial is congruent to 1, which is congruent to negative 1 mod 2. So we're good there. Now let's consider when n is equal to an odd prime. If n is an odd prime, then 1 times 2 times 3 all the way through to n minus 1 has an even number of multiplicands. So what we're going to do is that we're going to pair them off. 1 squared is, well, 1 times 1 is its own inverse, and n minus 1 squared is negative 1 squared, which is also its own inverse. But modulo a prime, modulo an odd prime, all of the other residues, they pair up. And I'll give you an example. If we have 7 minus 1 factorial, that's 6 factorial. And what we get is we have 1 over here, we have 6 over here, but in between we have a couple of pairs of factors. We have 2 times 4 and we have 3 times 5, and each of those are modular inverse pairs. This one is congruent to 1 and this one is also congruent to 1, modulo 7. And in general that's true. So what's going to happen is that n minus 1 factorial, we're going to have a bunch of 1s, and we're going to have 1 times n minus 1 left over, which is congruent to simply negative 1 mod n. So that takes care of the prime case. Next, we're going to move on to the composite case. So because it's composite, what we can say is that there exists a and b in the integers such that 2 is less than or equal to a, and a is less than or equal to b, and b is less than or equal to n minus 1, and ab is equal to n. Now, if we can choose A is less than B, then what this tells us is that A and B are both multiplicands of n minus 1 factorial, which is because we have this is 1 times 2 times 3 all the way through to n minus 1. And A is in here and B is in here. So this is congruent to 0 mod AB because A and B are distinct by assumption. And so A and B is n and we're done. But suppose we are forced to have A equals to B. Let's call that P. And you'll see why that's P in just a second. It has to be prime. It has to be prime. P is prime. Otherwise, there's going to be more. There's going to be some other factor that we can choose to be A. So P has to be prime. Otherwise, if it is composite, we can use an argument like this over here to get another factor in the zone between 2 to n minus 1. And not only is P prime, that implies that n is equal to P to the m for some integer m. It has to be a power of P. Otherwise, we're going to have another prime factor in this interval. And moreover, this has to be P squared. Otherwise, we would have another factor in this interval. So it really boils down to the fact that there's only one factor in the interval from 2 to n minus 1. So n is equal to P squared. We're going to split this into two cases. If P is equal to 2, then n is equal to 4. And what that means is n minus 1 factorial is congruent to 3 factorial, which is congruent to 2 mod 4. And if P is not 2, then that means P is greater than 2. We have some inequalities in this case. What we get is that 2 is less than P is less than 2P is less than P squared. All these are true and you should verify them. They're very easy to verify. Just cancel common factors. Then what happens is that we can choose this to be A and we can choose this to be B, and we get 2P squared divides n minus 1 factorial. So what happens then is that P squared is equal to n. So what that means is n minus 1 factorial is congruent to 0 mod P squared, which is equal to n. And just to be clear, P and 2P are both multiplicands of n minus 1 factorial. That's why this divides it. So in general, our classification works. This is our classification. So just as a recollection, it's -1 for primes, 2 for 4, and 0 for composite. Thanks for watching, and I'll see you next time.